Recurrent neural networks, RNNs, are a type of artificial neural network specially designed to deal with sequential data like text, speech, and time series, preserving the order of elements for analysis. Unlike feed-forward neural networks that process inputs independently, RNNs incorporate recurrent connections. These connections allow information to persist by looping the output of a neuron back as input at the subsequent time step, capturing temporal dependencies effectively. The core element of an RNN is the recurrent unit, which maintains a hidden state acting as a form of memory. This hidden state is continually updated at each time step based on the present input and the previous hidden state, enabling the network to learn from historical inputs and integrate that knowledge into current computations. RNNs have demonstrated success in various tasks such as unsegmented connected handwriting recognition, speech recognition, natural language processing, and neural machine translation. However, a challenge faced by traditional RNNs is the vanishing gradient problem, hindering their capacity to learn long-range dependencies. To counter this limitation, the long short-term memory, LSTM architecture, was introduced in 1997, establishing itself as the standard RNN variant adept at handling long-term dependencies. Subsequently, gated recurrent units, GRUs, were developed as a more computationally efficient option. Recently, transformers have gained prominence in sequence processing tasks, particularly in natural language processing, due to their self-attention mechanisms, enhanced capability in handling long-range dependencies, and improved parallel processing. Nonetheless, RNNs remain significant for use cases prioritizing computational efficiency, real-time data processing, or scenarios where the sequential nature of data is crucial. One origin of RNN can be traced back to neuroscience, where the concept of recurrent is derived from loop-like structures observed in anatomy. Notable findings in the early 1900s by scientists like Cajal and Laurent Deneau shed light on the existence of recurrent semicircles and recurrent reciprocal connections, respectively, hinting at the presence of feedback mechanisms in the brain. This notion challenged previous beliefs of the neural system being solely feed-forward. The McCulloch and Pitts paper in 1943 introduced the idea of networks with cycles, proposing the McCulloch-Pitts neuron model to explain how current activity in such networks can be influenced by past activities. Recurrent inhibition and neural feedback loops were further discussed in the scientific community, with researchers like Rosenblatt in 1960 delving into close-loop, cross-coupled perceptron networks, exploring the role of recurrent connections in learning scenarios. In parallel, the inception of RNN also finds roots in statistical mechanics, notably with the development of the Ising model in the 1920s as a simple statistical mechanical representation of magnets at equilibrium. Further advancements by Glauber in 1963 and Sherrington Kirkpatrick in 1975 contributed to the understanding of dynamic processes in systems approaching equilibrium, laying the groundwork for models like the Hopfield network. It was through these statistical mechanics principles that the Hopfield network with binary activation functions gained prominence in neural network studies, becoming a standard model for research in the field. Architectures like LSTM and BRNN have taken center stage. LSTM networks, pioneered by Hochreiter and Schmidhuber in 1995, have demonstrated exceptional performance across various domains, setting accuracy records and establishing themselves as the go-to architecture for RNNs. The advent of bidirectional recurrent neural networks, BRNN, further enhanced the capabilities of RNNs by processing inputs in both forward and reverse directions, leading to the development of the bidirectional LSTM architecture. This innovation significantly impacted fields like speech recognition, machine translation, image captioning, and language processing, outperforming traditional models and setting new benchmarks in these areas. As RNN technology progressed, the introduction of encoder-decoder sequence transduction in the early 2010s marked a pivotal moment in the field. The concept of CQ2-CQ architecture, utilizing two RNNs an encoder and a decoder, revolutionized sequence transduction tasks such as machine translation. These architectures became instrumental in advancing attention mechanisms and transformers, reshaping the landscape of machine translation and laying the foundation for further advancements in RNN technology. An RNN-based model consists of configuration and architecture. The configuration involves combining multiple RNNs in a data flow, where each RNN can have various architectures like LSTM or GRU. Abstractly, an RNN is a function that maps an input vector to an output vector, utilizing a hidden vector as memory to retain information from previous input-output pairs. Over time, it transforms input to output while adjusting its memory to enhance future processing. Practical neural network layouts often appear as layers due to unfolding across different time steps, not actual layers. A stacked RNN or deep RNN contains multiple RNNs superimposed on each other. In this setup, each layer operates as an independent RNN, with its output sequence becoming the input for the layer above, showcasing no restriction to the depth of stacked RNN. Moreover, a bidirectional RNN comprises two RNNs processing input sequences in opposite directions, merging their output sequences to provide a comprehensive output. By stacking multiple bidirectional RNNs, the model can grasp token context both before and after its occurrence, enhancing its contextual understanding. Furthermore, an encoder-decoder configuration involves running two RNNs front to back, with one encoding an input sequence into hidden vectors, and the other decoding these vectors into an output sequence, potentially incorporating an attention mechanism. This setup has been influential in developing top-notch neural machine translators, leading to the evolution of transformers. Additionally, an RNN can handle multidimensional data, as seen in Pixel RNN, which processes two-dimensional data in various directions. For instance, utilizing a diagonal by LSTM allows processing of a grid by LSTMs from different corners, adapting how they handle each vector based on their current hidden in cell states. A fully recurrent neural network, FRNN, features connections where all neurons' outputs link to all neurons' inputs, creating a fully connected network structure. This type of network serves as the most general neural network topology, as other network configurations can be simulated by nullifying specific connection weights to mimic non-existent links between neurons. An example within this category is the Hopfield network, characterized by equally sized connections across layers. While requiring stationary inputs and lacking the ability to process sequences of patterns, the Hopfield network ensures convergence and can function as robust content-addressable memory when trained using Hebbian learning. Elman networks and Jordan networks are also prominent in the realm of FRNNs. Elman networks consist of 3 layers arranged horizontally with an additional set of context units. These networks maintain a state by preserving past hidden unit values in context units through fixed back connections, enabling tasks such as sequence prediction that surpass standard multilayer perceptrons capabilities. Jordan networks, closely related to Elman networks, feed context units from the output layer instead of the hidden layer. Context units in Jordan networks, also known as the state layer, possess a recurrent connection to themselves. Both Elman and Jordan networks are typically referred to as simple recurrent networks, SRN. The mathematical formulations for an Elman network depict the hidden and output layer calculations at each time step to process input data and apply learning rules. In contrast, Jordan networks involve additional state calculations alongside hidden and output layer computations, further expanding the network's functionality. Key variables and functions in these networks include input vectors, hidden layer vectors, state vectors, output vectors, parameter matrices and vectors, and activation functions denoted by symbols like W, U, B, and sigma. Long short-term memory, LSTM, is widely utilized as a recurrent neural network, RNN architecture, addressing the vanishing gradient challenge by incorporating recurrent gates known as forget gates. This design allows LSTM to prevent the dissipation or explosion of errors during backpropagation, enabling the flow of errors backward through numerous virtual layers unfolded in space without limitations. LSTM exhibits the capability to learn tasks requiring the recollection of events that occurred thousands or even millions of discrete time steps earlier, showcasing its effectiveness in handling long delays between significant events and processing signals containing both low and high-frequency components. Variants of LSTM tailored to specific problems can be developed to enhance performance, leading to the emergence of deep LSTM when stacking multiple LSTMs, enabling the recognition of context-sensitive languages, surpassing previous models reliant on concepts like hidden Markov models, ChemM. The gated recurrent unit, GRU, introduced in 2014, serves as a simplified version of LSTM, offering comparable performance on tasks such as polyphonic music modeling and speech signal processing while requiring fewer parameters due to the absence of an output gate. Although both LSTM and GRU exhibit similar performance levels, with GRU having the advantage of a more straightforward architecture, the choice between the two is typically based on specific application requirements and computational efficiency. GRU variants, including further simplified versions, have been leveraged in various domains to achieve notable results, maintaining their status as popular alternatives to LSTM in certain scenarios. Furthermore, the bidirectional associative memory, BEM network, conceived by Bart Kosko, represents a variation of a Hopfield network focused on storing associative data in vector form. The bidirectional nature of BAM stems from the exchange of information through a matrix and its transpose, typically employing bipolar encoding for associative pairs to enhance network stability and real-world applicability. Recent advancements in stochastic BAM models, utilizing Markov stepping, have further optimized network performance, facilitating efficient recall of associations through input driving of either layer to produce an output, showcasing the network's bidirectional associative capabilities. Additionally, echo-state networks, ESN, feature a sparsely connected random hidden layer with only the weights of output neurons open to modification during training, making them proficient at replicating specific time series patterns. A variant of ESN designed for spiking neurons, termed a liquid-state machine, offers further enhancements for specific applications requiring spiking neural networks. On the other hand, recursive neural networks operate by applying a consistent set of weights iteratively across a differentiable graph-like structure, traversing the framework in topological order. These networks, often trained using reverse-mode automatic differentiation, excel in processing distributed representations of structural data like logical terms, aligning with applications in natural language processing. Particularly, the recursive neural tensor network enhances recursive neural network capabilities by incorporating a tensor-based composition function for all nodes within the tree-like structure, broadening the network's potential in capturing complex hierarchical relationships within data representations. Neural Turing machines, NTMs, are an innovative approach that enhances recurrent neural networks by connecting them to external memory units for interaction. This integration resembles a Turing machine or von Neumann architecture, yet it is unique as it can be fully differentiated, enabling efficient training using gradient descent. Further advancements led to the creation of differentiable neural computers, DNCs, an evolution of NTMs. DNCs permit the utilization of varying quantities of each memory location and maintain a record of the sequence of events. Additionally, neural network pushdown automata, NNPDA, bear similarities to NTMs, but they substitute tapes with differentiable and trainable analog stacks. This design aligns their complexity with context-free grammar recognizers. It's noteworthy that recurrent neural networks are deemed Turing complete, allowing them to execute diverse programs for processing a wide array of input sequences. In the context of training an RNN for machine translation without an attention mechanism, a technique known as teacher forcing is often employed to guide the generation of output sequences. The encoder portion of the model processes the input sequence of English words, while the decoder generates the corresponding French words. By utilizing teacher forcing, the decoder receives the correct output sequence during training to improve the accuracy of subsequent predictions. This approach mitigates the issue of error propagation, where mistakes early in the sequence could lead to further inaccuracies in the generated output. Gradient descent is a fundamental iterative optimization algorithm utilized in neural networks to minimize the error function by adjusting weights based on the error derivative. When training RNNs, the backpropagation through time, BPTT algorithm, is commonly used for gradient computation. An alternative method, real-time recurrent learning, RTRL, offers a more computationally intensive online variant that is non-local in space but local in time. RTRL's time complexity for computing Jacobian matrices per time step is O number of hidden X number of weights, contrasting with BPTT's O number of weights per time step. The challenge of vanishing gradients in standard RNN architectures spurred the development of LSTM combined with BPTT-RTRL hybrid learning, aiming to address this issue. The independently recurrent neural network, INDRNN, offers a solution by restricting a neuron's context to its past state, allowing cross-neuron information exploration in subsequent layers without gradient vanishing problems. The causal recursive backpropagation, CRBP, algorithm integrates BPTT and RTRL principles for locally recurrent networks, enhancing global error minimization and algorithm stability. This approach unifies gradient calculation techniques for recurrent networks with local feedback, providing a comprehensive perspective on addressing gradient-related challenges in RNN training. Connectionist temporal classification, CTC, serves as a specialized loss function tailored for training recurrent neural networks, RNNs, in scenarios where timing varies. The process of training neural network weights can be viewed as a nonlinear global optimization challenge. This involves creating a target function to assess the accuracy of a specific weight vector. Initially, the network's weights are adjusted according to the weight vector, and the network's performance is measured against the training sequence. Typically, the error of the current weight vector is determined by the sum-squared difference between the predictions and the target values provided in the training sequence. Various global optimization methods, with genetic algorithms being a prevalent choice, are then utilized to minimize this target function, particularly in unstructured networks. In genetic algorithms, the neural network weights are encoded in a predetermined manner, with each gene in the chromosome representing a weight link, consolidating the entire network into a single chromosome. The fitness function is computed by assigning each weight in the chromosome to its corresponding weight link within the network. The training set is then input to the network for signal propagation, with the mean squared error returned to the fitness function to steer the genetic selection process. Multiple chromosomes collectively form the population, leading to the evolution of numerous neural networks until a specified stopping criterion is met. Common stopping criteria may include achieving a set percentage of learning from the training data, meeting the minimum mean squared error threshold, or reaching the maximum number of training generations. The fitness function continually assesses the stopping criterion by receiving the reciprocal of the mean squared error from each network throughout training, with the genetic algorithm aimed at optimizing the fitness function to minimize the mean squared error. Alternative global or evolutionary optimization techniques like simulated annealing or particle swarm optimization can also be employed to discover an optimal set of weights. The independently recurrent neural network, INDRNN, was developed to tackle issues of gradient vanishing and exploding encountered in traditional fully connected RNNs. INDRNN allows each neuron in a layer to receive only its individual past state as context, promoting independence from the historical data of other neurons in the layer. This setup helps regulate gradient backpropagation, preventing the vanishing and exploding gradients, thereby maintaining long or short-term memory. Cross-neuron information is then explored in subsequent layers, enhancing the overall learning capacity. INDRNN demonstrates robust training capabilities with non-saturated nonlinear functions like ReLU and facilitates the training of deep networks through skip connections. The neural history compressor, on the other hand, functions as an unsupervised stack of RNNs. With a hierarchical structure, it predicts the next input based on previous inputs, selecting only the unpredictable inputs to pass on to the higher-level RNN. This allows for a compressed representation of information in each RNN layer, facilitating precise reconstruction of the input sequence at the highest level. By minimizing description length, or the negative logarithm of data probability, the system efficiently processes information. Through a careful distillation process into two RNNs, the conscious chunker and the subconscious automatizer, the model ensures that unpredictable events are correctly handled, enabling effective learning and long-term memory retention. Second-order RNNs present an alternative approach by employing higher order weights instead of standard weights, allowing for direct mappings to finite-state machines in both training and representation. While long short-term memory exemplifies this concept, it lacks formal mappings or proof of stability. Hierarchical recurrent neural networks, HRNN, excel in decomposing hierarchical behavior into subprograms, drawing inspiration from philosopher Henri Bergson's theories of memory. HRNNs prove valuable in applications such as forecasting, as demonstrated by the outperformance of the HRNN model in predicting disaggregated inflation components of the Consumer Price Index, CPI, against traditional methods based on a data set from the U.S. CPI-U index. A recurrent multilayer perceptron network, also known as RMLP network, is comprised of interconnected subnetworks, featuring multiple layers of nodes where each subnetwork follows a feed-forward structure, except for the final layer, which can include feedback connections. These subnetworks are linked solely through feed-forward connections. On the other hand, a multiple timescales recurrent neural network, MTRNN, serves as a computational model rooted in neural networks. It mimics the hierarchical functionality of the brain, achieving self-organization based on the spatial arrangement of neurons and different types of neuron activities, each characterized by distinct time properties. By incorporating diverse neuronal activities, continuous sequences of behaviors can be broken down into reusable elements, subsequently integrated into various sequential behaviors. This concept aligns with the memory prediction theory of brain function as proposed by Hawkins in the book On Intelligence, and also resonates with Henry Bergson's memory theories, both of which have been integrated into the MTRNN model. Moving on to memristive networks, these systems involve a cortical computing framework utilizing memristive nanodevices. Memristors, constructed from thin film materials, allow for electrical resistance tuning through ion or oxygen vacancy transport within the film. The development of neuromorphic architectures based on memristive systems has received support from DARPA's Synapse project, involving collaborations between IBM Research, HP Labs, and the Boston University Department of Cognitive and Neural Systems, CNS. Memristive networks exhibit similarities to Little Hopfield networks with continuous dynamics, limited memory capacity, and a natural relaxation mechanism through function minimization akin to the Ising model. Their dynamics offer advantages over resistor-capacitor networks, showcasing intriguing nonlinear behavior. Engineering analog memristive networks represents a unique facet of neuromorphic engineering where device behavior is influenced by circuit wiring or topology. The analytical study of these networks' evolution can be approached through variations of the Carovelli-Traversa-di Ventre equation. A continuous time recurrent neural network, abbreviated CTRNN, uses a set of ordinary differential equations to simulate how incoming inputs affect a neuron. Often analyzed through dynamical systems theory, many recurrent neural network models in neuroscience work in continuous time. In the network, for a neuron labeled as I with an activation y sub I, the change in activation rate is given by the equation alpha sub I times ab I sub I equals negative ab I sub I plus the summation from j equals 1 to n of w sub ji times sigma of I sub j minus theta sub j plus I sub I of t. In this context, alpha sub I represents the time constant of the postsynaptic node. I sub I stands for the activation of the postsynaptic node, and y dot sub I represents the rate of change of the activation of the postsynaptic node. Additionally, w sub gi denotes the weight of the connection from the presynaptic node to the postsynaptic node. Sigma of x is the sigmoid function defined as sigma of x equals 1, divided by the quantity 1 plus e raised to the power of negative x. E sub j signifies the activation of the presynaptic node. Theta sub j represents the bias of the presynaptic node, and I sub I of t indicates the input, if any, to the node. CTRNNs find applications in evolutionary robotics, where they have been utilized for tasks related to vision, cooperation, and minimal cognitive behavior. As per the Shannon sampling theorem, discrete time recurrent neural networks can be seen as continuous time recurrent neural networks, in which the differential equations have been converted into equivalent difference equations. This transformation occurs after the postsynaptic node activation functions, YITT, have been low-pass filtered but before sampling. RNNs are considered as recursive neural networks with the structure of a linear chain, working on the linear progression of time by combining information from the previous time step and a hidden representation into the representation for the current time step. From a time series perspective, RNNs can be viewed as nonlinear versions of finite impulse response and infinite impulse response filters, as well as a nonlinear autoregressive exogenous model, NRX. RNNs possess infinite impulse response, contrary to convolutional neural networks that exhibit finite impulse response. Both classes of networks demonstrate temporal dynamic behavior. In the context of memory-based learning for sequence recognition, a more biological-based model incorporating the silencing mechanism observed in neurons with high-frequency spiking activity can be implemented. Stored states and network-controlled storage can be added to both infinite impulse and finite impulse recurrent networks, while another network or graph may replace the storage if it includes time delays or feedback loops. These controlled states, referred to as gated states or gated memory, are integral to long short-term memory networks, LSTMs, and gated recurrent units, also known as feedback neural networks, FNN. Various deep learning frameworks offer optimized runtime implementations for enhanced performance. For instance, Apache Singa and Caffe were developed by the Berkeley Vision and Learning Center, supporting both CPU and GPU with implementations in C++ and wrappers for Python and MATLAB. Chainer provides full Python support for tasks such as distributed training on CPU and GPU. Deep Learning 4J enables deep learning in Java and Scala on Spark with multi-GPU capabilities. Flux, written in Julia, includes interfaces for recurrent neural networks like GRUs and LSTMs. Keras functions as a high-level API, acting as a bridge to numerous deep learning libraries. Microsoft Cognitive Toolkit MXNet is an open-source framework designed for training and deploying deep neural networks. PyTorch offers tensors and dynamic neural networks in Python optimized for GPU acceleration. TensorFlow under the Apache 2.0 license resembles Theano, but includes support for CPU, GPU, and Google's TPU. Theano, a Python library, aligns its API closely with NumPy for deep learning tasks. Torch, a scientific computing framework written in C and Lua, also integrates machine learning algorithms to further diversify the available tools in the deep learning landscape.